So there are many ways in cosmology to describe distances between 2 points. Why is this? This is because the universe is expanding. Because of this, we have different distances in cosmology, and we're going to talk about these. We're going to talk about 4 of these distances. We're going to talk about proper distance, comoving distance, luminosity distance, and angular diameter distances. So first talk about the proper distance. D for distance, and we're going to make a little, mark it with a little p on the bottom, stretches over time in proportion to the expansion. So here we have a galaxy, okay? And here we have another galaxy. Then we have the distance between them here. This is the distance, the proper distance at a time A. We have like a measuring scale here. Now some time passes, and after some time has passed, the space between these two has increased. They moved away from each other due to the space between them increasing or expanding. And I have this distance. So in case of the proper distance, the scale doesn't actually change. We just use the same scale as before. It expanded, and this is now the proper distance at time B, at a later time. This corresponds more to our conventional understanding of time, of distances. Did I say time? I mean distances. So this here is basically fixed at a certain time. It's a fixed scale. The scale stays the same, as I said. So dp increases over time. As the universe expands, but it is a theoretical distance. We cannot measure it. How are we going to measure it? The light travels to the universe while the universe is expanding. So we can't measure it on the scale. So it can be derived due to cosmological models. So you need a cosmological model to derive it. And now we're going to go to the comoving distance. And we go back to the topic of scale. And the comoving distance we notate as d with a little c. With the comoving distance, we see here the scale hasn't changed, right? And for the comoving distance, the scale is changing with the expansion. So we use a coordinate system that is stretching proportionally with the expansion. That means the distance remains constant as the time, and therefore the scale is stretching, right? So the distance remains constant because the scale is stretching. So we have now 2 galaxies here. We draw the same thing again. There's one galaxy here. And one galaxy here. This is the comoving distance now. At the time A, we have here again the scale at this time A. So now again, the space between these galaxies is expanding. So they're gonna be here now. Here's the galaxies here. The other galaxies here. They're farther away, so the distance is now the comoving distance at time B. But now the scale doesn't stay the same. So what we have here now, here and here and here and here. Okay, so we combine this, yes. So we have now a scale that is increasing with the expansion. And now we can have add a scale factor. So we have now the proper distance at a certain time. And we add the scale factor multiplied with the comoving distance. we call a scale factor. We call it, this is an A, we notate it as A. And this describes the scale of the universe. Yeah, it describes the scale of the universe as it is expanding. So over time. That is the comoving distance. What happens to nebulas or planets on a time-space stretching plane? It doesn't matter because locally it is irrelevant. So the space that is increasing is not actually, for example, increasing between us, Earth, or like the sun. So it's locally bound, gravitationally bound. So everything that is gravitationally bound is gonna stay gravitationally bound. Like, even though we're expanding, the Andromeda galaxy is still gonna crash into us. Doesn't matter. So now we talked about the proper distance, the co-moving distance. And now we're going talking about the luminosity distance. D and L. This is determined by comparing the apparent brightness to the absolute brightness. Do you remember what the apparent and absolute brightness is? Who remembers that? Who was here last time? So, determined by comparing apparent to absolute brightness. Just a small m to absolute brightness. And this is called magnitudes. We note this with a capital M. These are magnitudes. There's like apparent magnitude, how bright something appears to us, and the absolute magnitude is basically how bright it would actually appear to us when we would be like 10 parsecs away from that object only. And we are going for the luminosity distance. We compare these both. It's really just a very simple fact that light gets diluted over distances. We have a star here. It shines outwards and it illuminates. So it's an imaginary circle that gets illuminated by the light. Now, if the light travels a farther distance, this imaginary sphere is suddenly bigger, right? And the same light has to now illuminate a much larger area. So the photons get diluted. So, and for the space-time, the effect of expansion has to be added towards this calculation. So the luminosity distance, then the proper distance at a certain time, 1 plus z. We're going to talk about the z later. Normally, we wouldn't really need this. We could just do this with the distance modulus, and I write that down here, where we compare, this is the apparent brightness, apparent magnitude, absolute magnitude. But now we're talking about like expansion and cosmology, so it's not going to be that simple formula anymore. So that is the luminosity distance. And now the last one of the 4 distances I wanted to explain to you, and that is the angular diameter distance. dA, okay? d8 is the angular diameter distance. So if we have the observer here, like this is us, there. And here we have the galaxy. That is the size of the galaxy here, right? This is the actual size of the galaxy. So we notate it with S. And this is the distance from the galaxy to us. This is the angular size, angular diameter distance. Here's the angle. And normally we could just derive it with the simple geometrical relation. But the thing is, when that light was emitted, we were way closer to that galaxy. We were way closer to that galaxy. So when that light was emitted, we were closer, and hence this is not actually the distance today. This is the distance how it was when it was emitted. When the light was emitted, the universe was smaller, so the angular diameter distance was also smaller. So what we're actually measuring is the past distance, Now this leads to some funny things. It means that with increasing distance, the objects will appear larger. If you look in the distance, very far away, then the object, the light that arrives, means that actually they now would be way far away from us. This is kind of like a magnifying effect. And that also means that at the beginning, when we measure the distance, the angular diameter distance will increase at the beginning for closer objects, right, locally. But then it will start decreasing. So dA will increase for closer objects, but decrease at a certain point. So this is irrelevant for you now. This is just redshift 1.6 1.6 is like this cutoff point, but we talk about this later. We learn about the redshift later. So locally, we measure the distance to a galaxy in angular diameter. And then we're going to measure the distance to a galaxy that is further away, and the angular diameter distance will increase, right? It will be larger for a galaxy farther away. But at a certain point, when space-time becomes like more relevant, the distance will start to decrease, because when the light was emitted to us, the object was closer. So we are measuring the path distance. Then we have the angular diameter distance equals the proper distance times the scale factor A. We use this for the proper distance to connect it to the comoving distance, and then again for all the other distances. So consider a homogeneous sphere that is either contracting or expanding. Expanding, right, this direction, or contracting. That would be this direction. Radially. It's like symmetrically expanding or contracting radially. We draw a bigger sphere here. This is the sphere. We are introducing a coordinate system here, and we choose a point here, x, point x, and this is at the point t0. T0. Now this is a particle. Let's say we're going to put a particle here, right? And now this is expanding. So the sphere is expanding. Yeah, you just like a balloon. We're blowing up the sphere. Does this point x is now here? This is now here, and it radially, always in the same direction. Yeah, it moved radially out in the same direction. So we are calling this r now. We're calling it r now. At a time t. So time passes, it expands, and that particle is here now. Expansion is radial. So the direction of r, it's a function of t, is constant. At this point, at the point t0, right? So at the point t0, r equals x. So that means that the scale factor is 1 at this point, which means at point t0, the scale factor must be 1. A of t is the cosmic scale factor, a function that changes over time, and it was 1 at t0. So r t0 is 1 times x equals x. Stands for the relative size of the universe and is normalized as, so if a is 0, that is the Big Bang. If a is smaller than 1, that is the past. If a equals 1, that is the present. And if a is bigger than 1, that will be the future. the recession velocity or radial velocity, in this case, VR, of the comoving particles can be defined via the Hubble parameter. This h of t, it's a function of time. And what we have the time derivative of the scale factor divided by the scale factor. So for the people who have never seen this, if you put a point on top, this is the time derivative. And this formula is the Hubble flow or expansion rate. The change of proper distance between two co-moving regions is called the recession velocity. It's not like that this one galaxy, even though it seems they're moving away from us, what really happens, we are both increasing, we are both moving away, like both co-moving particles move away from each other due to the expansion of space. So, and this can be then derived via the expansion scale parameter. So this is the co-moving distance. Or we can then also use the Hubble parameter and put it in terms of proper distance. We have complex conditions in the large-scale universe. So there is no trivial distance measurement, and it requires application of complex cosmological models. I will hit you with the expansion equation. You don't have to remember or understand. I just wanted you to have, so that you have seen it. Okay, so we have here the scale factor squared. This is the Hubble parameter. We're going to talk about this later on again. This as a cosmological parameter. So 4. This is another cosmological parameter. More cosmological parameters. Or in short, that's what you do, right? You just give it another letter so you don't have to write everything again all the time. And this is like the dimensionless Hubble function. Okay, so just that you have seen it. When I'm talking about for lower scales, we don't have to use it. But the moment we're going to higher distances, like very larger distances, and we're gonna talk about the cutoff points later, but because I want to define it in terms of redshifts, then we have to use these cosmological models with these complicated equations. It's nice. It's really cool shit if you have to work with it and actually have to use it. You realize how well this actually all works out. It's pretty awesome. We're going back to lower scales, right? This is what we have to do in cosmology. And now when we go like to lower scales, where we can use simplifications, this simplification of the Hubble law was found by Hubble and Lemaître. So it's called this law. It used to be only called the Hubble law, but they found out that this is not true. That it needs to be attributed to both of these guys. It was found in the 1920s. Yeah, I'm not used to that either, because when I started studying, it just became a new thing. Like at the beginning when I learned it, it was only the Hubble law. And later, it became the Hubble-Lemaître law later. So yeah, in the 1920s, both of these guys derived this law independently of each other. And this is also nice. This shows you how awesome science is, right? They derived it independently of each other. Here, this is an empirical. So it comes from observed data. Linear relation. So between the distance and recess velocity. And the Hubble constant, H0, is the proportional factor. We have the recess velocity times d, and we call this the HL distance, Hubble Lemaître. So that is the recess velocity, or the radial velocity. That's the distance, and that is the Hubble constant. Given in usually kilometers per second and per megaparsec. What we talk about linear relation, that means if this is the distance at this axis and here's the velocity, that means the faster they move away from us, the farther away they are. That's a very simple relation. And this applies only for nearby sources. So basically what we have here is the Hubble constant is the Hubble parameter at that time. We can use it for smaller distances because all the other distances start out in a linear way. So I want to draw this here. Like for example, this is time now, and this is distance. So we talked about the angular diameter distance, and we talked about how this decreases when we look farther out. So it starts linear too, the angular diameter distance. The angular diameter distance starts out linear, right? And then it starts decreasing. It starts decreasing. And the Hubble is constant, and it's also starting out linear, but then it continues linear. Which is not really that true anymore in the end. But at this part, for this smaller distances and smaller times, we can just use it. Now we're talking about redshift. Or the z value. When we talk about redshift, we always mean the z value. When you look at astrophysical stuff and you see the z, that's the redshift. That's what we're talking about when we talk about redshift. This is the only measurable variable in terms of cosmology. When we measure the distance, we measure z. Or we measure z and we measure the distance. But we can always only measure the redshift. Hence, z is independent of the cosmological model. It can be measured from the shift in spectral lines. So we need a relation between z of a source and the cosmic time, or the scale factor, at which the source had the light emitted. First, I want to tell you what a spectrum is, because we talk about the shift of spectral line and you have no idea what a spectrum is. First off, the emitted light. How about a picture? You want to see a picture? There, guys. I feel it's time for a picture, okay? Time for a picture, so you see something nice. Different colors of light have different energies and wavelengths. We're talking about the shift of a spectrum. What we mean if this is a shift in wavelengths, right? A certain color emitted as light has a certain wavelength. So the visible light is in between 400 and 700 nanometers. The scale here is in nanometers. And in the ultraviolet light, we have like shorter wavelengths and higher energies. And in the infrared light, to the reds, we have longer wavelengths and lower energies. So when you look at a galaxy, you are actually looking at a combination, or more like superposition, of all the light emitted from the stars. You see a superposition of the light from millions of stars. Yeah, we're gonna talk about the types of spectra, okay? So this is just in terms of colors. And like a spectrum of a galaxy consists of 3 different types of spectra. 3 types of spectrums. So the first is the continuous spectrum, or you can call it smooth spectrum. And what we look at is the energy distribution over these wavelengths, right? So we have, here's the flux, that we measure the flux. That's the light that is arriving from the star towards us. And this is the wavelengths, and which I probably should have done and I didn't. We notate the wavelengths. Did I write wavelengths here? So wavelengths is notated with lambda. So when we write lambda, the small lambda, we mean wavelengths. So that's what we mean here. So we have a continuous spectrum that the energy distribution is looking smooth. Okay, that's the continuous part of the spectrum. It contains all wavelengths emitted by a hot source. This depends also on the temperature. Like a star has a certain temperature and it emits at that temperature. So stars has different colors, and the colors also depend on the temperatures. Continuous spectrum of a star is close to the black body radiation. So if we have the diagram here, so a star that appears more blue is more hot. So the continuous spectra will look like this. So our sun is more like 5,000 kelvins. Okay, like let's talk this in kelvins, I guess. So the temperature will be about 8,000 Kelvin. Let's say that here. And a star, it's more like yellow, right? And it's more in the yellow, and then it will be under this, and this will be like 5,000 Kelvin. If the star appears red, this is a very bad drawing, by the way. It's like the worst drawing ever. Oh, I hope you get the idea. And this is about 3,000 Kelvin. So just that you see that if a star has a different temperature, it radiates a different continuous energy distribution, and it will look differently. So now we have the absorption spectrum. Coordinates, I'm so sorry. This is the flux. And this is, again, the wavelengths. So, I don't know. There's UV here, ultraviolet. And in here we have infrared. And in here we have the visible light. Okay, now we have the absorption spectrum on top of that. And the absorption spectrum will have absorption line within this continuum. So, right? Oh, sorry, flux, wavelengths. Oopsie, sorry. We're gonna have a nice picture of that. Don't worry about it. I found a nice picture. So you see, there's light missing. There's light missing in the continuum. So absorption lines, they're getting absorbed. Missing light within the spectrum. Why is that? Because the starlight passes. So we have the star here. So let's see, we have the star here. And the light is passing through a cloud. Okay, so we have a cloud here. And the light that comes out, some of the light is getting absorbed by the elements that are within this cloud. So the gas cloud absorbs some of the wavelengths, certain wavelengths, depending on the elements within the gas. So a hydrogen atom, or hydrogen or like helium atom, or whatever other element you have, will absorb at different wavelengths. They will not absorb at the same wavelength. That's basically how we want to find exoplanets. We want to look through the light that's going through the atmosphere of these exoplanets, and we want to look at the absorption lines. What kind of light gets absorbed by that atmosphere? Now, the star has an atmosphere too, right? So a star, if you just look at a star, and you also see absorption lines, it's a mix, because a star has an atmosphere, and this atmosphere also is made out of elements, and the spectrum will then look something like, okay, there you go. there you go. So this is like the spectrum of a star will be a combination of the continuous spectrum and the absorption line. The spectrum of a star will be a combination of both of this. It will look somehow like this. But this is like a typical spectrum of a star where you can see some hydrogen lines. You can see you have like a continuous spectrum here and you have absorption lines. Okay, so that was two types of spectra, and now we're talking about the spectrum that is interesting us today, and that is the emission spectrum. The emission spectrum. So that is what we are interested in today. The continuously emitted energy from a star, the continuum, so the light emitted by the continuum of a star or any source, but we say star, okay, can heat up its surrounding gas. So we have the star here, and that is, we had this drawing also last science stream, so maybe you can remember. So not only have we like absorbed light coming out of this, if you look from this direction, but if the cloud itself can now shine with emission because of it's heated up by the star, by the continuous energy from the star. So atoms and molecules within the cloud get excited and start emitting light on their own. The atoms within the clouds absorbing the photons coming from the source or from the stars, the electrons get on excited energy levels, and then eventually they're gonna get de-excited again and releasing the photon again. And this way we can see the emission. Yeah, we have some nice hot ionized plasma and we can see it. All right. So the spectrum of a galaxy is a composite spectrum of stars and gas within the galaxy. So these three spectral types I just talked about, you see this all. You see this all within the galaxy. So the emission line spectrum will look like this then. Instead of absorption lines, we're gonna see emission lines, right? Spikes. So we will look at the nebula and we see, oh, it's emitting at this certain wavelengths because of this certain element, right? So there's gonna be hydrogen atoms within the clouds, and at certain energy levels that get excited and then like de-excited again, they emit the light, and we can see these emission lines. You can just make a theoretical spectrum in the computer with models how it should look like, and then you can like fit these models onto this spectrum. That's how it's usually done. You have a library of different kind of all the different types that could there be, spectrums that could there be, and then you just fit them towards the spectrum, and this way you can like separate it. We're gonna now draw the conclusion to the redshift from these emission lines, yeah? So these emission lines here, this is what we're gonna look today. Like, this is interesting as today. This is how we later look with the James Webb Space Telescope data. The Z value is derived from the shift of these spectral lines due to the expansion of the universe. While of course the whole spectrum will shift, the shift of the emission lines, this is what you can measure because you can recreate it in the laboratory on Earth and know exactly what emission lines you're looking for. You know the numbers, so you can recreate this. So we go back to the sphere here. Let's see, we have a wavelength in here, right? We like, this is light, the light is within the sphere. And now we have the universe expanding, so it's getting bigger. And it's stretching the light. It is stretching the light. The wavelength is getting longer. It's getting shifted towards the red, because we have learned here the red has longer wavelengths, right? 700 nanometers. It's given in nanometers here. I think 1 nanometer is like 10 million centimeters or something like this. Longer wavelengths is towards the red. So because of the expansion, the light gets stretched, it gets longer, so it gets redder. So the light we receive is looking redder than before. So the wavelength is stretching proportionally to the expansion. Here you see like a shifted spectra over the redshift. This is 3 spiral galaxies. One is at redshift 10, the other is at 11, the other at 12. And you see that the more it's shifted, like the older it is, the farther away it is from us, it is getting shifted to the red, right? So the spectrum of a galaxy that is farther away from us, it's shifted more towards the red. And now we're gonna have to combine this with the scale factor. So it lets us the cosmological scale factor, A of t, just by measuring spectroscopic data, spectral lines. And how is it connected? The scale factor is connected by this very simple formula here. And here you can also see these emission lines, right? There are different kinds of emission lines. It's like one here, one here. It's the same line, it's just getting shifted. And this line has a laboratory value. It has a value it actually should be. And that is, we call this emitted. This is lambda emitted. That's the value it had when it was emitted. And we compare this compared to lambda observed. And we derive the z value. Wait, you can't see that anymore. We derive the z value by comparing the emitted line with the observed line. Z0 means at t0, that is nowadays. So that is the present, or like, present. Z infinity basically means Big Bang. T0, T was 0, no age, the universe was just born, Big Bang. We're going to use now the Hubble law. We're going to use this to derive the distance towards the galaxy. Yeah, if you have a second monitor, you can now use the link I will give to you. So we're going to go to this website. We are going to go to the MAST portal. That's where you're going to go. And when you're on the site, you're going to go on advanced search on top, right? Advanced search, this is where you click on. Click on advanced search. You're greeted with this. You're going to click here in project and you click JWST. And in my case, I was looking for a cube. So I click that too in here. And then you wait until this is loading in. This is basically, you can look for images, spectrum, or cube, or measurements. You see it found 1339. We click now on search. I filtered by MIRI, NearSpec, but you can like do with different filters here. Also, you see a lot of stuff is locked, like you see all the yellow stuff is locked. You can filter by parklip. You can now type in NGC as a filter word and filter by names. Then I looked for a galaxy and I decided for this galaxy, NGC 7319. Okay, so if you filter by observation ID, what you have to find so you can see the same as I see is this one. And if you found it, you click on this little icon, the blue spectrum icon, and you click on display. You're gonna go to a new site and they will give you the spectrum. And bam, you're in the James W Space Telescope data. So this is basically the spectrum, right? And what we learned earlier, we look at the spectrum of a galaxy. I could probably give you the picture of the galaxy, what we're looking at. Yeah, let me do this. There you go. That is the galaxy we are looking at. So first off, the wavelength is a micrometer. It's not a nanometer, a micrometer. But let that not distract you. It doesn't really matter. you see here now the whole stacked up spectrum. What you can do, you can, for example, if you want to change the units, if you click on the right here, you can just change the units conversion. You can do a whole lot of stuff, but what you can also do, and that is very interesting, if you click here on define a circular region, and then you look for a region in that galaxy, for example, like let's only look at the center region. I think I can move it. Yeah, so now we're only looking at the center region. So we click on the home button here, and now we see on the bottom the red spectrum. This is the spectrum only stacked up from all the spectrums from the central region. We can see it's lower in energy because it's less spectrums than before, right? And it looks a little bit different. It looks a little bit cleaner, and we can also just, for example, look at one pixel if we want to, right? We click on here, and we click like on, I don't know, that pixel here. We will not be, you see now, it's barely visible. You can zoom in. If you click on the zoom tool here, you can zoom in. And now you have like a better understanding. So now we are looking at a pixel, at this teeny tiny pixel on that, and the spectrum and the galaxy of this pixel. Okay. So what we're trying to find now is the spectrum, and that's the pixel I chose. 2520. So X should be 25. By the way, you can delete this if you click here on the section. You click on finding the pixel. So we click on this pixel view and we try to find pixel X25 and Y20. Yeah, try to find this. 25 and 20. Oh, damn, I didn't click here, damn. Okay, I clicked it. Now we click on the home button here. How does it look? How does it look? Yeah, so I'm in it's now a light blue. If you like cannot see it after you shows the pixel, you have to click the home button, and then you have like the zoom and draw the area over the small line, and then this is the spectrum we're looking at. Okay, so this is the spectrum we are extracting, and these are the emission lanes we are going to look at. You see this on your screen now, and we are gonna go to a different type of data. The same data, but I downloaded data and put it into Python, so I can make it visibly better for you. Blank. So that is the spectrum in a different manner. I extracted it from it. Now we're gonna have to look for the emissions line. You see some emission lines, and we have to basically identify them. I just looked up which emission lines should be there. You expect different emission lines depending on what you look at. Yeah. So I put the emission lines in for you. There you go. So it looks like this now. And what you see here, the spectrum is shifted. The spectrum is shifted, and the emission lines are drawn at their rest frame position, right? So you can see that this is helium, this is argon, this is magnesium, this is iron, another magnesium line. You can see here these lines, if we shift this spectrum, because this is redshifted, if we would shift it back, if we would correct it for the redshift, then these would probably the emission lines we would find. Let's remove this again. And this again. And put in here. I put in some numbers. This is in nanometers, by the way. Yeah, this is in nanometers. And now we're going to calculate. We're going to calculate. You should be able to see this yourself, the number yourself. You should be able to see the number yourself in the JWST. If you put the mouse over it, you should see the wavelengths. Even if it's in micrometer, it doesn't matter. You can just convert it. So the original emission line, so emitted, of this Argo line, right, is 6985 nanometers. But we are observing it at 7141 nanometers. That is where we are observing it. And now we are using this formula for the redshift. So let's calculate this. 7.1. And you can tell me if you come to the same numbers, okay? So we can all see if this is all right. 6985. And we divide it by 6985. And what it, so I get this, I get the number 0.022 and let's say 3. The Hubble law was this, and we replace the radial velocity with the speed of light times z. And now we rearrange these formulas to this simple formula. The speed of light, what is the speed of light? It's 2997992 kilometers per second. Now let's find the Hubble constant. We're gonna look up the Hubble constant. You just go to Wikipedia. So we just use the newest one. We have like from 2022 using supernova, and from 2021 using Cepheids and supernova from the distance ladder. So let's just use this value. So we have the Hubble constant, we have the speed of light. So let's derive it, okay? Let's derive the distance. 2999792 kilometers per second times the z value. Let's make this. The z value is 0.0223, and we're dividing this by the Hubble constant, 73.4 kilometers per second in megaparsecs. So we're gonna get this in megaparsecs. So calculate this times 0.0223, 73.4, 91.08 megaparsec is the distance to this galaxy. Okay, shall we find out if we calculated something that could be true? Okay, shall we find out? This is the galaxy here, NGC 7319, and the distance. Okay, we have an entry for the distance, 59.3 megaparsecs. This is the source. Let's click it. What's it? It's from 2011. Okay, so this is from 2011. 2011, the distance was, I guess 2011, they probably used a different Hubble constant. What was the Hubble constant 2011? Like 70 or 69. So what if we calculate this with 70 instead? 59. What do you know? Okay, so if we would use the Hubble constant from of 70 from like 2010, then we would get the same result as they got here, 59 megaparsec. But because the Hubble constant changed, we are having a different result. Okay, so there is a limit to using this Hubble law, and that limit, the limit to the Hubble law, is Hubble law limit is for redshifts smaller than 1. If we go to redshift higher than 1, we have to use the cosmological models we looked at earlier. We can use cosmology calculators. Let's actually try out our value. We got 003. No, wait, what? 023. Okay. And click calculate. Like the cosmological parameters, I just use what they have in here. I'm sure like you can look up current cosmological parameters. Cosmological parameters also change. Okay, so we gave in the redshift from our galaxy, and we're getting a shorter angular diameter distance. Makes sense. Luminosity distance a little bit larger also makes sense. And we're getting a comoving radial distance of 91. Okay, guys. So I guess we did everything correct. Okay, so that is what you do to derive the distances. With the Hubble law, we could calculate it for the other wavelengths too to see if it's correct. We calculated this for the argon line, right? This is for the argon line. Let's calculate the second one for the magnesium line. Okay, yeah. Let's do it for the magnesium line too. So Z for magnesium. 610. It's actually slightly different, but this is okay because you have always errors in this kind of spectrums. So that's what I'm deriving it. So maybe my measurement was wrong. I didn't use very precise numbers. I haven't even plotted the error yet, right? There's usually also, when you download the data cube, there is an error within the data cube. You can like look at the errors as well. Yeah. I hope you learned something today. I hope it wasn't too much. It might have been a little bit too much, but I really wanted you to get an idea of how complicated all of this is. I didn't just want to show you the Hubble law and say that's how you do it. I wanted you to realize that it is more complicated than that, but that we can simplify things for our like proximate areas. That was really a lot. Let's go through all of this again. Yeah, we started with the Friedmann, Lemaître, Robertson-Walker matrix, that you know what people talk about when you hear it. And we went through all the distances: proper distance, comoving distance, luminosity distance, angular diameter distance. I explained to you what the scale factor is, the cosmological equations together with the scale you have to use later for the cosmological model. The Hubble-Lemaître law, and I explained to you what the spectrum is, what the spectrum is made of, and how this connects to the redshift. And we derived here in calculating the distance for galaxy NGC 7319. And we even concluded to a different distance because we used a more recent Hubble value. Like, even if you didn't understand all of the formulas, it isn't the point that you understand all of the formulas. My point was more to you get an idea how they do it, and that when they talk about, hey, this galaxy is this far away, now you have an idea in your head. Okay, and this is maybe how they came to the conclusion of how far the galaxy, how far away the galaxy is. So now you have something popping up in your head. Thank you so much for attending. I very, very much appreciate that you attended the science stream, guys. And until later, guys, live long and prosper. Bye-bye.